Hello, everyone, and welcome to the OneClass channel. My name is Donna, and I'm a recent master's graduate in the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So I also got my Bachelor's of Science at this institution as well in pharmaceutical chemistry. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you had any problems with homework or you needed some tutoring, then check out the links in the description below. So now I'm just going to get started on our set of questions for today. Alright, so question number 1 asks, a laser pulse with wavelength 532 nanometers contains 3.85 meters of energy. And then they ask, I guess it's millijoules of energy. That doesn't make sense. So millijoules of energy, how many photons are in the laser pulse? So first I'm just going to write down everything that I know. I know that, the wavelength of the laser pulse is 532 nanometers. And I'm also just going to convert this to meters, just so that everything is in the same units. So it'll just be 532 times 10 to the negative 9 meters. And we also know the energy of this laser pulse. I'm going to put energy of pulse, and it's 3.85. And I'm assuming that this is millijoules. But I'm going to convert this to joules. So it's just going to be 3.85 times 10 to the negative 3 joules. And then this is in the laser pulse. Okay, so we know the wavelength. So this is like a two-part question, because first we are going to calculate the energy of a single photon. So this energy is different than the energy of the laser pulse, because the question asks how many photons are in the laser pulse. So first we're just going to figure out how much energy is in a single photon. And to do that, we use the equation E equals hc over lambda. So h is Planck's constant, and its value is 6.626 times 10 to the negative 34. And its units are joules times seconds. So this is why I converted everything to joules, just so that we can use constants like this. Same goes for the speed of light, which is our next variable c. So the speed of light is 3 times 10 to the 8, and its units are in meters per second. So this is why I converted the wavelength to meters, because I can just plug it in right now. At the bottom, the wavelength is 532 times 10 to the negative 9 meters. So now, if we solve for this, you'll notice that the units cancel out pretty well. The seconds cancel out here. Meters cancel out as well. And then we're left with an energy value of 3.74 times 10 to the negative 19. And then this is in joules. Okay, so that's the first part of the question. When we want to calculate for the number of photons, it's actually going to be the energy of the pulse, the laser pulse, divided by the energy of a single photon. So all we have to do is plug in those values. So it's going to be 3.85 times 10 to the negative 3 joules. And this is divided by 3.74 times 10 to the negative 19 joules. So these joules will cancel out. And for the number of photons, we end up getting 1.03 times 10 to the 16, I believe, photons. Okay, so let's see the answer from our junior tutor. They said, to calculate the number of photons present in the laser, the number of photons present in the laser is, the energy of the laser is, this looks like it's missing a lot of important information that needs to be filled in the blanks. So I'm just gonna write out what I did. First, we need to calculate the energy of a photon using E is equal to hc over lambda. Well, I'll put wavelength. Guess I'll just put in the values. I'll just put these in square brackets. Which is equal to 3.74 times 10 to the power of negative 19 joules for number of photons E pulse over E photon is equal to then I got 1.03 times 10 to the 16 photons. Okay, so we can move on to question number 2. Diethyl ether has the following structure. Which groups of protons are equivalent to each other? And then how many signals are expected in the HNMR spectrum? Okay, so first let's write down the structure of diethyl ether. You'll see that it's like symmetrical. And I can actually draw like a plane of symmetry right in the middle of the oxygen, just to help us visualize this molecule. Okay, so when we want to find out which groups of protons are equivalent to each other, we want to first look at the neighbors. And also the chemical environment of each photon. And what I mean by that, let's say we're looking at the protons in this first carbon. I'll label them A. If you look at the neighbors, it has a carbon with 2 other hydrogens. And you can say the same thing for these hydrogens over here. If you look at what it's attached to a carbon with 2 hydrogens. So let's look at the hydrogens beside it. This CH2, it has 2 neighbors. One of them is an oxygen, and one of them is a carbon that has 3 hydrogens. So we can say the same thing for this set of hydrogens right here. And you can see that the hydrogens in A and B are different from each other. So when we answer the question, which groups of protons are equivalent to each other, it's going to be A. Well, actually, I'll just follow the labeling that the question gives, just so that we're all on the same page. But I'll keep it the same colors. Okay, so if we look at which of them are equivalent, it's going to be A is equal to D, and also B is equal to C. So therefore it's option 3. Now let's look at the second part of the question. How many signals are expected in the H NMR spectrum? So we have 2 distinct sets of protons. Therefore, the number of signals will be 2. So it's going to be this kind of proton or this kind of proton. Okay, let's check out the answer from our junior tutor. A equals D and B equals C and 2. Note 2 signals, one is from CH2, the other one from CH3. So solution is correct. Okay, so now let's move on to question number 3. Which of the gases in the graph below has the largest molar mass? So let's try to mimic this graph. On the x-axis, we have molecular speed. And it goes from 0 to 2,500. And then on the y-axis, it's the relative number of particles. I'm just going to like roughly sketch out what the graph looks like. We have a big kind of like a peak. There. This is D. And then C is like similar, except it's a little shorter. B is shorter than that. Kind of goes up like that. And then A is like this long heap right here that covers a lot of the molecular speed. So just by analyzing the graph, you'll notice that D has the most number of particles in one spot, and it's like near the 500 range in the molecular speed thing. So therefore D has the largest molar mass. And let's say we weren't given this graph and we were only given like there's molecular masses and we had to estimate which one would be the slowest and the fastest. We can also remember that the molar mass is inversely proportional to the speed, which makes sense. You can also write it as like largest particles are slower. So in this graph, A would be the fastest, and we can also tell because the number of particles ranges from like 0 to 2,500 molecular speed. So let's see the answer from our junior tutor. D has the largest molar mass. So this solution is correct. Okay, so moving on to question number 4. How could you separate lauric acid from alpha naphthol? So if you were to look up their properties on like Google or something, or I like look at their MSDS, then you'll see that lauric acid has a low melting point. At around like 45 degrees Celsius. And this alpha naphthol its melting point is like very high. It's around 121 degrees Celsius. So therefore we can use cycles of like heating and cooling to try and separate the two solutions. Let's look at the answer from our junior tutor. The melting point for lauric acid is about 45 degrees, while it is 121 for naphthol. Yep, that's what I got. So in a mixture, repeated cycles of slow warming and cooling should separate the two. You can improve the efficiency by adding a dash of slightly acidic 70% isopropanol. This will deprotonate the lauric acid while maintaining the proton on naphthol during this process to enhance separation and purification of the two compounds. It also flat out distill the two products by maintaining the temperature of the solution at the boiling point of lauric acid to separate it from naphthol. That was a long sentence. This might also be a good polishing method. So that's cool. So this solution is correct. And now let's move on to question number 5. Draw the additional resonance structures of the structure below. Okay, so question 5, I'm going to draw out the structure that they gave us. It's like this cyclohexane-ish ring with a ketone, a double bond right here. And then you'll also notice a pair of electrons right there with a negative charge. So these arrows indicate that I'm about to draw a resonance structure. So first I'm just going to show like the movement of electrons that can occur. So this pair can move onto that carbon. To form a, actually they can form a double bond right beside it. And then from there, this double bond will transfer the electrons onto the carbon that is right beside it. So one resonance structure will end up looking like this. We have a new double bond right there. And then we have the pair of electrons right there. So another thing that we could do is like go in the opposite direction. So we can make a double bond back where it was before. But this time this double bond will move here. And then the double bond on the oxygen will then move up and give a negatively charged oxygen instead. So finally, we'll have two double bonds located there. And then now we have single bonded oxygen with a negative charge. Let's see the answer from our junior tutors. Okay, so they have it going this way to give what is also the same as my last structure, and then they have it going back down to give the same thing as my second structure. So this solution is correct. Okay, so moving on to question 6. We have 3 different aqueous solutions, and they just ask, which of the following scenes best represents how the ions occur in an aqueous solution? Okay, so this is question number 6. So before I look at all the different options, I'll just note that we are going to separate into their ions first. And what I mean by that is, let's say we have magnesium chloride. You'll see that there are 2 chlorines for every 1 magnesium. So magnesium had a 2+ charge, and chlorine has a -1 charge, but there's 2 of them to neutralize that magnesium. Then we can do the same thing for this sodium sulfate. Separating it into its ions gives us 2 positive sodium ions, each with like a 1+ charge. And then this sulfate ion has a 2- charge. And then lastly, we have ammonium bromide. Separating this into its ions just simply gives us a positively charged ammonium ion and a negatively charged bromine. So now let's look at the different options they give us. So for A, this blue and yellow kind of solution, you can see that there are like there's 1 negative charge for every 1 positive charge. So this best represents C, the ammonium bromide. And then let's look at B. So we have in the purple and green solution like a +2, and then for each +2 there are 2 negatively charged ions. So this is similar to what we have with the magnesium chloride. There is a magnesium that has a 2+ charge and then 2 chlorines. So solution B is with that one. And then just by process of elimination, let's also double check C. There are like 4 very large negatively 2 charged ions. And then for each one, there are 2 small like positively charged ions. So this is similar to the sodium sulfate. Okay, so let's look at the solution. They have it separating to Mg2 plus 2Cl represents B, represents C, and then the ammonium bromide represents A, since anions and cations are same in number. So this solution is correct. Okay, so let's move on to question number 7. What is the volume of 5.6 grams of oxygen at 7.78 atm and 415 Kelvin? Please show all work? ? Okay, so first I'm going to write down everything that we know. We know the mass of oxygen, and it is 5.60 grams. I'm actually also going to write the molar mass of oxygen, which is 16 grams per mole. And it's always good practice to just calculate the number of moles from there so that everything is in order. So to calculate number of moles, it's going to be the mass over the molar mass. So plugging those values in, 5.6 divided by 16 grams per mole. Our grams cancel out, and mass of O2 is not 16, it's 32, because there are 2 oxygens. Always double check your work. And you should end up with 0.175 moles of O2. What's also given is the pressure. So we know pressure is equal to 7.78 atm. And we're also given the temperature in Kelvin already, so you don't have to convert anything. And then the equation that we want to use is PV equals nRT. So this is a very commonly used equation. It's for ideal gases. Doesn't say in the question, but we are going to assume that it is an ideal gas, and it's just like oxygen. So we are looking for volume, and we have pressure, temperature, number of moles now, and for R, it is just the constant. So there's a lot of different R constants, so just be aware and make sure you use the right one. So for this particular question, I'm using 0.08205, and that's because it's in the units that I'm looking for. So I know I have liters times ATM. I also have a mole and K. So that is why I have chosen that value for the R constant. Okay, so if we rearrange the PV equals nRT equation, we can solve for volume, which is just going to be nRT over pressure. And then I'm just going to plug in what we have. So 0.175 moles. This is going to be multiplied by this gas constant, which is in liters times atmosphere times mole per K. And then temperature is just 415 Kelvin. All of that is going to be divided by pressure, which is 7.78 atm. Okay, so now you'll notice all the units should nicely cancel out. So that's how you know that you have the right R constant, if all the units cancel out nicely. So this will give us a final volume of 0.769 liters. Let's look at the answer from our junior tutor. We will use the classic equation PV equals nRT. P is pressure, V is volume, N is moles, R is gas constant, T is temp and K. Plug in what you know, so then they also found the number of moles, and they got 0.769 liters. This solution is correct. And then I'll just put a disclaimer, assuming O2 acts as an ideal gas. Okay, so moving on to question number 8. Draw tryptophan and select the chiral carbon atom. Okay, so I'm going to draw tryptophan over here. So tryptophan's an example of one of the amino acids. Basically, it's one of the ones that has like a 2-cyclic structure. The first cyclic structure is like a benzene ring. And then attached to it is like a 5-ringed like amine. And then from here, I'm going to draw out the rest of my amino acid. So every amino acid has like a carboxyl group. They have an amine group. And what's not shown is like the hydrogen up here. And what makes every amino acid different is that they all have like a different R group. So in the case of tryptophan, it's the only one that will have a different R group that looks like this. Okay, so now it wants us to select the chiral carbon atom. So let me write down the definition of chiral. So the chiral carbon atom will have 4 different groups on carbon. So if we try to find it in this structure, you'll notice I will highlight it with an asterisk. It is right here. Because it has the nitrogen group, it has the carboxyl, it has a hydrogen, and then it has the R group on the left. And then I'll just also name this. It's going to be L-tryptophan. And let's see the answer from our junior tutor. Okay, so they have the carbon that is in green. They have NH2, the COOH, the hydrogen, and then they also have the tryptophan R group. So this solution is correct. Okay, so moving on to question number 9. Water is known as a polar molecule because, and then it gives us different like options. So first I'm just gonna write down the water molecule before we get into the specific options that they give us, just so that we're all on the same page. This is the water molecule. And oxygen is more electronegative than these 2 hydrogens. So I'm going to draw that it has a dipole moment going in the direction of the oxygen. Let me also put in the lone pairs here. So because oxygen is more electronegative than the 2 hydrogens, the molecule has a slightly like negative side. And then on the side with the 2 hydrogens, they're partially positive. So this is the reason why water is polar. Let's look at all the different options that they give us. They have 1, the oxygen atom has a greater attraction for electrons than the hydrogen atom does. So this solution is correct. 2, the oxygen and hydrogen atoms have the same electronegativity. So we know that this is false, since oxygen has a higher electronegativity than the 2 hydrogens. 3, water has 2 hydrogen atoms covalently bonded to a single oxygen atom. So this is true, but it's not the reason why it's polar. I don't know if it's like a trick question, but I'm just gonna say true. But not a reason why it's polar. For the electrons of the covalent bond are not shared equally between the hydrogen and oxygen atoms. So this is true. And it's also one of the reasons why water is polar. For 5, the hydrogen atom attracts electrons much more strongly than the oxygen atom. So again, we know that this is false, since O2 will attract them more strongly. And then let's look at the last option. Water dipole moment is equal to 0. So this is also false, since water has a non-zero dipole moment. So dipole moment is kind of like similar, but it's the same thing as the arrow that I drew up here. You'll see that it's pointing in the direction of the oxygen. So if we had a non-polar molecule, I'll just show for comparison. Not only do they all have similar electronegativities, but also the hydrogens are all pointing symmetrically in like different directions. So this is an example of a zero dipole moment, since they all cancel each other out. So this CH4 is a non-polar molecule. Let's see the answer from our junior tutor. Sorry. Can't see that. Okay. They said the correct statements are that oxygen atom has a greater attraction for electrons than the hydrogen atom does. Yep. And then electrons of the covalent bond are not shared equally between the hydrogen and oxygen atoms. So that is also correct. So this solution is correct. Okay, so let's look at question number 10. It's kind of at an angle. But basically it says sodium bromate is used in a mixture which dissolves gold from its ores. Calculate the mass in grams of 4.68 moles of sodium bromate. So this is a pretty easy question. So first I'm going to look up what its molar mass is, just to save us some time. Okay, so sodium bromate has the chemical formula of NaBrO3, and its molar mass is 150.89 grams per mole. So the question is asking us for calculate the mass in grams of 4.68 moles. So we know that the moles are equal to 4.68. And all we have to do is use this equation where its mass is equal to molar mass times the number of moles. So plugging all the values, 150.89 grams per mole multiplied by 4.68 moles. And if you always get confused about which one's on top, is it the little m or the big M, or which one do you divide by, you'll notice that all your units should cancel out nicely. If you're looking for grams, then that means all the moles should cancel each other out. And then we're left with a value of 706.17 grams. So it is option number 2 in the question. Let's see the answer from our junior tutor. It's like a businessy related. So I'm just going to write down what I did. So this is like a simple high school type question. Okay, so I said we know the moles of sodium bromate is 4.68 moles, and we know its molar mass is 150.89. Therefore, we can use M equals big M times N to get 150.89 times 4.68 to end up getting 706.17. So sorry, that solution was incorrect, since that was a different answer altogether. Okay, so that brings us to the end of today's Q&A session. If you liked today's video, then go ahead and leave it a like and a comment. And if you'd like to be notified of when we do this next, then please hit the subscribe button and the notification bell below. If you had a question of your own that you'd like to submit, then check out the links in the description. And also don't forget to share it with all your friends and classmates if they needed any help with chemistry. So this has been Donna from OneClass, and I hope to see you soon. Bye.